And we're live. Hello, everyone. My name is Justin Jeffress, and I am a PyTorch DA at Meta. And I have a special guest with me today, this Will Constable. Will, would you like to introduce yourself?
Thanks, Justin. Yeah, I'm a tech lead at PyTorch team at Meta, and I work mostly on PyTorch compilers and also at the intersection of compilers and distributed. So that's what we'll be talking about today.
Great, yes. And this is the first PyTorch Live 2.0 QA of 2023. So happy and excited to kick off this year's content. And so just a little bit of background, in December of 2022, PyTorch 2.0 was announced, and that brought a lot of really interesting and cool features, one of which is torch.compile. And so today, Will is going to be talking about some of the cool things that you have at your disposal in order to bridge the gap between using PyTorch compile with distributed, specifically with DDP and FSDP. So Will, let's dive into the topic.
All right. So, as Justin mentioned, when we started working on Torch compile mostly works on the single node or single machine side of things. It works on making an optimized version of a program like on a GPU or CPU, but it doesn't account for how to scale that across multiple machines. And a lot of our users care a lot about scaling across multiple GPUs, running bigger models than you could fit on a single machine. And so we need a way to make PyTorch 2 run in a distributed training environment. So if you're not familiar with DDP or FSDP, I'll talk a little bit about what those are. But the point here is that PyTorch 2 introduces huge speedups on single node, and we want to be able to combine that with DDP or FSDP for a faster distributed training. So this wasn't actually all that easy to do. There's a few challenges that came up as we tried to plug these two technologies stacks together, and it was actually a lot of fun to try to work through these challenges. And that's what I'll be talking mostly about today is what the problems were at first and how we mitigated them and how we solved them. And I'll dive right into that now. So the first part of my talk is going to be about the background on these components, like what is PyTorch 2, how does torch compile work at a very high level, and then what are the distributed challenges, the distributed technologies and like the challenges putting them together. And then I'll dive deeper into specifically DDP and FSDP. Also, I just want to say, if you have questions, jump in at any time. I'll try to respond on the chat, and I'll try to respond to the questions that come up on the chat. And Justin can also help call things to my attention. If we're running short on time, I'll mention, I'll try to just keep going forward at that point.
Yes, and I'll stop before we get started. Somebody, I don't quite know how to pronounce your name, Maher. Sorry if that's incorrect, but he was just asking: is PyTorch 2 released yet?
PyTorch 2 is not officially released. The code for PyTorch 2 is evolving on our nightly branch, and the nightlies are available to be installed via pip, or you can build from source. So you can already try this stuff out, but the official release hasn't happened yet.
Yeah, so you can definitely get your hands on it in the nightlies, but yeah, it hasn't been officially released yet. So cool. All right, so let's dive into the
Yeah, I'll dive into this slide. The Torch Dynamo is the front end for PyTorch 2. And what it does is it acquires graphs out of Python programs. Python programs aren't really that friendly to a compiler because they can do so many different things and they're so flexible, which is one of the reasons PyTorch users like using Python. But we need a way to kind of construct a simplified straight line graph out of a PyTorch program and feed it to a backend. And that's what Torch Dynamo does. So one of the fundamentals of PyTorch, another fundamental of PyTorch is autograd. Autograd is the thing that calculates derivatives and comes up with backwards formulas for your program. And one of the things that autograd supports is a plugin called an autograd.function, which is a way where you can you can define a new operation in PyTorch and supply both its forward and backward component or functionality and plug that into AutoGrad so that when somebody's running a PyTorch program, like AutoGrad engine can call the backwards part from your custom functionality. And Torch Dynamo actually builds on top of this AutoGrad function as a way to integrate with eager PyTorch. So we didn't want the compiled mode of PyTorch to be a very foreign experience. We wanted it to be seamless and integrate very nicely with eager PyTorch. And eager PyTorch, by the way, means kind of the old world of PyTorch where you call one operation after another in Python. There's no compiler, and it's flexible, it's dynamic. When you introduce a compiler, we wanted it to be possible for programs to be partly compiled, have the compiler fall back to executing maybe unfriendly parts of the program in eager PyTorch. And so the integration works by producing compiled programs and stuffing them inside of AutoGrad.function boxes. And then these boxes can kind of integrate with the eager PyTorch runtime.
And so are those boxes what you're referring to in your diagram up here with the F1, F2, B4, B3?
Yeah, so if you think about a PyTorch program being a series of like forward operator 1, 2, 3, and 4, and then backwards operators go in reverse, so 4, 3, 2, 1. You might compile just operators 2 and 3 together into a chunk, and that would be replaced by this compiled forward and compiled backward object. And then you can see down below, this is actually what happens when you execute the program. There's a eager operator for F1 still running, and then there's this compiled forward for the fusion of F2 and F3, and its backward also shows up as a fusion for the backwards of 3 and the backwards of 2, and those compiled artifacts get executed by the eager runtime, just like they were a native operation in eager PyTorch.
Cool. And are these running like, I might be getting ahead of us here, but are these running like in parallel, or like, are they in sequence?
No, this is time left to right. So this is just a single machine view of the world so far. No distributed stuff yet.
Okay. So this is before we've scaled.
Yeah. So then now jumping into distributed a little bit, perhaps the most basic distributed technology is data parallel. You don't have to think too much about changing your model. You're basically saying, I want to run the same model on a bunch of machines, and then each machine is going to process different input data. But the only catch is you have to synchronize or communicate between the machines periodically to make sure that they're gathering their shared work back together into like a shared state of the new model. So they're all working together, updating the weights of the model. And so DDP implements this data parallel algorithm by doing these all reduce operations that are communicating the gradient updates between machines. And this communication is a kind of a blocking operation that happens where all the machines have to communicate at the same time. If one of them starts sending out weights and the other one hasn't started listening for those weights yet, it wouldn't make sense, right? They all have to be, you can think of it as all of them getting on the phone together and like sharing some data. If somebody's late, they all have to wait for the late person. So these all reduce operations happen in a blocking way. And in order to make it faster, DDP tries to overlap all reduce operations with backward compute. So that's what this diagram is trying to show, is that after you've gone through the forward pass of your model and the backward pass started, if you finish the backward pass for a single layer, which is one of these smaller boxes, then you can start communicating that layer's gradients while you compute the next layer and so forth. So you can overlap the blue boxes and the gray boxes. And that's basically all DDP does. It's the overlap and also bucketing. So grouping together multiple small layers into one bigger chunk. So you don't send a lot of small messages. You can send a fewer number of bigger messages. So those two things are the main parts of DDP. And so plugging DDP into PyTorch 2 or torch.compile, we suspected right away that there's going to be a problem because, as I mentioned earlier, the autograd.function object that represents a compiled program is essentially an opaque thing from the perspective of eager autograd, and all of the backward operations for that compiled program happen all at once, and there's no chance for these all reduce operations to overlap anymore. So we end up making the backward compute and the forward compute faster, but not allowing overlap for the communication anymore, which in some cases actually still could be faster, but could also be slower, and definitely is parasitic to the advantage of compiled PyTorch. So we really want to bring back this overlap of these all reduce operations. And while I have this on the screen, I also wanted to show the way you compose DDP in Torch Dynamo is that you first just wrap your model in DDP, and then you pass the DDP model to your compile. And I forgot to update this picture. It should say torch.compile instead of torch.dynamo.optimize. That was our old API, but it's the same thing.
Okay, great. Yeah, so that you were referring to the code that was in the upper left-hand or right-hand side.
Right. Yeah. So
yeah,
how can we fix this? There were a few ideas that came up. One of them was to trace DDP's communication operations into the graph. And another one was to rewrite DDP as a compiler pass. But both of these were a little bit hard to do, in part because we don't have communication operations available in a way that's traceable or supported by our graph IR yet. And so we thought, okay, well, what if we just break the forward and backward compiled programs into pieces so that there's now gaps again for overlap to happen? And this actually turns out to be a pretty good solution because the optimizations that the backends in Torch Dynamo do, or Torch Inductor, typically optimize local regions of the program. So they're fusing together parts of a layer that are near each other in the graph. They're not fusing things that are really far away in the graph together. So breaking the program down into relatively large chunks actually doesn't cost us much performance or any performance, and also does allow this DDP overlap to come back into play. And meanwhile, we still want to support traceable collective ops, but that doesn't have to be a blocking pull. We can actually enable those over time.
I see. So you're basically, you have a multi-step solution here. And the first step was to split everything into smaller chunks that are closer to one another. So that way that is being more efficient in the way that it's building the models.
Yeah. So the graph splitting started out as like maybe this is a short-term solution, but as we investigated it and prototyped it, it turned out to be a pretty good solution. And we found that the performance was great. And I think it's still like tempting to grab a whole graph and try to use traceable collectives. So we're going to add support for traceable collectives, but that's not a big deal anymore for DDP, especially because DDP's performance with split graphs is really good. So now I'm going to talk more about how the graph splitting works and like show some data and walk through the code a bit. So in order to do the graph splitting, Dynamo has to determine, first of all, when this part of the program that it's compiling is even a part of a DDP program. And so we do that by detecting Well, Dynamo is already doing some analysis of the Python frames to determine what to do with the code and like how to generate a graph out of it. So it already has to know quite a lot about the program. And so it's not too hard for it to just look at the forward. If it's getting a forward function as a frame, then check if that forward function came from DDP. Is the forward function DDP's forward function? We can put a simple branch there and say, like, if it's not the DDP forward, we just go through the normal compile flow. And if it is the DDP forward function, we feed it to a special optimizer that's going to then go and do this graph breaking logic. And the logic itself is pretty simple. It's basically, as I mentioned earlier, DDP has this bucket concept where it's going to put some of the layers gradients together into buckets and group them so that it can do more efficient communications. And so we just need to know what the logic is for these bucketing, for DDP's bucketing, so that we can break the graph up in the same way that DDP produced buckets, and we can produce kind of matching graph breaks that allow the DDP communications to interleave between them. And so I'll show the code for this in a bit, but the gist of it is to take a single graph for forward and then split it up into multiple graphs for forward. One more thing I'd like to point out here is that it might not be very obvious why we're talking about forward, because DDP's communications all happen during backwards. And so it's true that we really want the backward graphs split. And the way we achieve that is by splitting the forward graphs, which is a little counterintuitive, but it's because of the way Dynamo works with autograd functions. It's already creating one big forward graph and one big backward graph that go together. And so by splitting the forward graph in the right places, we're also splitting the backward graph in the right places.
I see. So is there like is there a way to avoid splitting the forward graph if you need or want to?
So that's a good question. Actually, several people have asked me that before on GitHub. And currently there isn't a very good way to do that, at least not the way Torch Dynamo is designed, because of using autograd function like this. But if we do want to avoid graph breaks, we could do something where we use traceable collectives, which would be coming later. And then we could include the collectives into the graph and compile one whole graph that includes like forward and backward and collectives.
Great. And that leads into another question that somebody from the community asked. Karan, apologies if I didn't get your name right, but they ask, what does it take to enable traceable collective operators?
Yeah, so this is a little bit of this is a little bit annoying, frankly. The idea of traceable collectives is really simple. So, and there's one more requirement, which is that they need to be functional. We need to have functional collectives so that we can trace functional operators into our graph. Our compilers like functional graphs. They don't like operators that are mutating their inputs or acting as in-place operators. And so I break it down the answer into two parts. We need a functional collectives, which we don't have today. And then the collective APIs we do have today also have these process group objects as a part of their API. And that's something that would have to be either redesigned or Torch Dynamo and in our graph stack needs to be able to understand how to handle those objects. And then they also return these work objects that are kind of like futures. And so those also need to be dealt with throughout our whole stack. And so it's in theory, it's a simple thing to do, but it's actually a lot of work in practice to change these APIs. And so we're going through a phase of designing like what the right API would be and how do we bring that to the system.
Cool. So in short, it's not supported today, but it's being thought upon and people are working on trying to figure out a good solution for it.
Yep, exactly. So let's see. Next, I want to do a demo. So I'm going to dive into the code editor and Justin, if anyone has questions while I'm doing this, I probably won't see it, but you can call it out. So what I'm going to show is I'm going to run a couple of models. Like I have this code that's a benchmark script that I basically wrote for testing purposes. So it's kind of a toy model. The first one I'm going to run through. It's this model that has a bunch of, it has like 12 layers that are just big linear layers and linear and ReLU. So it's a simple model that we can understand what it's doing. And I'm going to be running this with DDP and showing what happens without the optimizer and then applying the optimizer. So the without optimizer case is this first command here. I'm going to run the toy model with DDP, and this is just to show you what the output of the model is. It's just going to tell you that like it's run 10 iterations and it took a certain amount of time. And so that's cool, but it doesn't tell us that much. Now I'm going to add the profiler, and this is going to let us get a glimpse of what's wrong with the communication overlap, which I hinted at earlier. So now we've got a profile trace, and I already downloaded these traces earlier, so it's a little easier to get them into my browser. So this is the no optimized trace. You can see I've got 10 iterations of forward and backward, and I'm going to zoom in on the first iteration of just forward and backward, and I'll search for all reduce. So you can see that all of the all reduces that are showing up in this trace are happening towards the end of backwards. And we don't want that. We want them overlapped. Oh, I'm also not showing the GPU kernels themselves because this is a single node, and so the kernel is probably not even running. But these CPU side pink boxes here should be overlapped with the compute in order for the kernels to be launched in parallel. And so this is the root cause of this is the root of the issue that we're trying to fix, is getting these all reduce kernels interspersed with the compiled function here.
Right. Referring back to your original diagram where you had like the different things all like in serial, now you're basically just like combining these together, and they're sharing resources rather than blocking.
Yeah, exactly. So then if I run that first command had go ahead.
Real quick question. Someone was asking in the chat, Karan, is the script that you're presenting in this demo available somewhere on GitHub to play with and experiment with?
Yeah, these like 5 commands aren't actually in a script anywhere, but the code that they're running from is all on PyTorch master. So I'm not running anything special. The stuff that you're seeing besides these command lines are all part of PyTorch. You can just run them locally.
Cool. Yeah. So if you take a screenshot, you can have these commands at your disposal, and you can type them in. But yeah, it would. So yeah, like there's nothing.
We can post the script.
Yeah. Cool.
So so the first command had this like flag that says don't optimize DDP, since it's now the default, and so it's kind of the inverse. Like now by deleting that flag, we're going to optimize DDP. So that's the third command here, and if I run that, then we should get another profile trace, and I'll show what that looks like. So here again, we have the 10 forwards and backwards, but if I zoom in this time, you can see things look a little different. If you kind of compare before and after, you can see on the before, it's a bunch of backwards up, a bunch of autograd stuff on the right and a compiled function backward on the left. And in the new trace, you've got you've got the same AutoGrad stuff on the right, but some of it is actually broken up and interleaved towards the left and mixed into the backward segments. So if we search for all reduce again, we can see that we got one all reduce happening way back here at the beginning and one here in the middle. And then there's another compiled function. This is like this box here is a compiled function backward. And this is an all reduce. So in theory, this should be exactly what we want. We've still got compiled functions and we've got all reduces happening in between them. So just a couple other things I want to show on the code. I'm going to show you some debug output that explains a little bit like a little bit more in detail what's happening. So with the verbose option here, you can see a bunch of stuff will get dumped out, but the one thing I'm going to look for is there's a table that gets dumped out by the graph split optimizer. And that table shows you the index here is the number for the graph or the DDP bucket. The size is how many parameter bytes got grouped into that bucket. And then this shows you the names of the parameters or layers that went into that bucket. So this is helpful if you're trying to debug like what happened with my graph split, or why is it splitting more or less times than I wanted it to. And so like in this case, you get a couple of parameters, a couple of layers on the first graph because DDP has this algorithm to start one all reduce early, even if it's small. And then after that, you try to fill up larger buckets. And that's sort of why you get so many layers grouped together there. And you can also see the original graph. This is a view of the original graph. All the different call module nodes here correspond to calling those layers in the toy model I showed you earlier. And then the split graph calls into 5 different submodules, which each one is like one of those compiled chunks. Mm-hmm. And each of these submodules contains like some portion of the original graph. So you can see the submod 0 breaks down into this graph, which contains net 0 and net 1. Submod 1 contains like net 1, 2, and 3. And so that's how this works. You can see into the graph transformations and diagnose anything that might have gone wrong, or understand, just at least understand how to tune the performance better or change the bucket sizes.
Yeah, and I had 2 questions that came up from that. So like, is it normal to see some overlap? Like there was a couple there where the several different graphs were in the different submods. So is that something that you would expect to see?
Oh, sorry. Which ones are overlapping?
I think it was the submod 0, the target selfnet 1, and then in submod 1. Oh, actually, that is the reference to the submod. Never mind. Okay, I misread that.
It's true that the name like net 1 shows up in these 2 graphs, but in this case, it's kind of like it's the output of the first one and the input to the next one.
Right. Yeah. Okay, that makes sense. And then, you mentioned like optimization and performance. How would you, from this graph, like be able to, or is this the right place to look at for like optimizing and measuring performance, or is that something is there a better resource to look at for that?
Yeah, so the 2 tools for this are this view and also the profiler. And the knob you can turn is in the code for what is that file called? Distutil. Somewhere in here, there should be a thing that applies DDP. I'm looking at distutil.py, which is part of this benchmark I told you about. And I think it's actually in distributed.py, which is the outer benchmark script.
Right. So here we go. You're DDP referring model. To code that's part of the PyTorch repository. This isn't code that wasn't written. Yeah, like this is part of the core.
That's right. This is all part of PyTorch. And so DDP itself has a parameter called, what is it called? Bucket cap NB, somewhere in the middle of the screen here. The default is 25. So going a little bit off script, but if I change this to, let's say, something really big, and then I rerun my demo, hopefully we would actually see something different. So let's see what happens. So here we go. So we still got one small chunk at the beginning because, like I told you, DDP always prefers to start a small I'll reduce because there's some overhead and it's trying to work around that. But then after that, it grouped all of the remaining parameters together into one big bucket. So instead of getting like five subgraphs,
I see.
Now we got 2 subgraphs, and this is what the split looks like.
I see. And so is there advantage to having more or less subgraphs? And is the answer have to do with like, it depends?
Yeah. So from a compiler perspective, I guess you want less subgraphs because you, in theory, can only take away opportunities for the compiler to do optimizations by splitting the graphs smaller and smaller. From the DDP perspective, you might want more and more subgraphs because you want more chances to overlap communications. So you're looking for a kind of a happy medium between the two. And the way you decide is just by checking on the profile trace whether you've got much time where there's an all reduce happening that's not overlapped behind any compute.
Right. Okay. I think this answers Karan's next question, where he says that, or he asks, is this split meant to be automatically chosen? Would a user ever have to tune any of the parameters to augment partitioning of the graphs? And so I think you just demonstrated, modifying that partitioning by adding that max cap parameter.
Yeah. So this parameter here isn't something new for the optimizer for PyTorch 2 or for Dynamo. This is like an existing tunable parameter that DDP users would already be familiar with. So basically what we're doing with the graph splitting is we're honoring whatever the user set here and trying to make the graph splits match these bucket choices.
Cool. And then one more question. This comes from, I imagine it's pronounced Javi. Again, apologies, I mispronounced your name. And the question is, does using PyTorch.compile with the full graph option eliminate the Python overhead, for example, with Numba?
So torch.compile eliminates Python overhead from the parts of the program it can compile, but it can only compile parts of the program that manipulate PyTorch operators that are part of the Torch library. It doesn't understand like other extensions that are written in C++. Those look like opaque kind of objects to it. So it just has no choice but to like call into those, or to, in some cases, if we're exiting the region that we can compile and calling into some other library, we'll just have to break the graph and then produce some output tensors and then feed those into the other library.
I see. Yeah. So if it knows how to do it, it will. If it doesn't, it just leaves it as is, and like you said, calls into it and pipes that output into the next part.
Right. Yeah. And there's the full graph mode doesn't make Torch Dynamo able to deal with anything more. It just makes it so that it's explicit. So if you want to make sure you're capturing a full graph, you set full graph mode, and then these cases become errors where they'll stop you and they'll flag your attention. They're like, hey, this part I couldn't compile. But in the normal mode without full graph, it's the same. It's just that Dynamo will then kind of transparently fall back to calling into those parts, and it'll compile the parts that it can compile.
Cool. Yep. That makes sense. If it knows how to compile it, it will.
Yep. All right. So I think that's all I was going to show on the demo. I guess I can also walk through the code briefly if I open up
Sure, yes. We're at about 35
Torch,
minutes, so I don't know how much more other content you have to get to, but just want to give you a quick time check.
yeah, I'll just do this for a couple minutes and then I'll go back to the slides. I think it'll be perfect.
Great.
So this is the main class that does the graph splitting. It's in Torch Dynamo and it gets enabled automatically when you're running DDP, and it's basically got three parts. It computes the partition map in order to match the DDP bucket logic. So this part is kind of like a traversal over the FX graph that came from Torch Dynamo. The second part is to actually apply that information into splitting the original graph into multiple smaller graphs. And this is where the split graph module that we saw in the debug dump came from. And then the third part is like this compiler that actually feeds each of those subgraphs into the backend compiler, like Torch Inductor or whatever other compiler the user actually wanted to use. So that's all I was going to say here. Like the code is there if you want to look at it. And so with that, I'll go back to the slides. I'm going to talk a little bit about the benchmark results we got with DDP. So on the left, I have a picture showing what things looked like without the DDP optimizer. And we're reporting speedups here. So 1.0 is just breaking even. And you can see a lot of the data points on the graph are actually below 1.0. And the color codes show us the number of nodes. So you can see that the blue ones are typically a lot higher. So single node here is 8 GPUs and 8 nodes is 64 GPUs on 8 machines. So the more nodes you add, the more communication time takes, and the more like these all reduces become a significant part of the program time. And so for I think for almost every model we tried, we started with a speed up on a single GPU with Torch Inductor, and we ended up with a slowdown on 64 GPUs with Torch Inductor. And so we really wanted to fix this. So we want to make it a clean win-win story. Like you can use both together. And so that's what the optimizer actually does, is on the right graph, you can see the speed up again with the optimizer turned on. And so in this case, we're in all cases above 1.0, and it's a much tighter distribution, like in terms of scaling up. So as we add more GPUs, you can keep the performance advantage of Inductor longer and longer. Also, there's a blog post linked down below, and I think it's been posted with the, I guess like with the other announcements for this talk. So go check that out. One of my colleagues, David, wrote this post and went into a lot of detail about like how we worked through this and how we did the benchmarking, et cetera. So I'm going to dive into the next part of the talk now on FSDP. Let me know if there's any more questions on DDP. So FSDP is, we're good?
Yes.
Yeah, FSDP is like another data parallel technique, but one that's targeting larger models that don't fit into the memory of a GPU. And so it does some of the same stuff as DDP in backwards, and it also has some new, more complicated things that it needs to do during forwards, because what it's going to try to do is actually make it so that each GPU doesn't have to keep a full copy of the layer's weights, and therefore can fit bigger models. But like right before using a layer or going through the forward function of a layer, FSDP has to gather the full state for that layer from all of the peer GPUs. So now you've got, in FSDP, there's an all gather right before forward, and then after forward, you can free or delete like the rest of the weights that you don't, besides the shard you're responsible for. And then during backwards, when you get back to the same layer, that's what this diagram's showing. There's another all gather, so we can restore the full state of the weights locally, and then do the backward operations, and then reduce scatter to put the gradients back on the piers where they go. So there's a lot more communication going on here, and a lot of it's blocking and time critical, or could be blocking if it wasn't orchestrated well. So FSDP has to do a bunch of, I would say, almost magic to try to orchestrate this communication so that it's not getting in the way. And it does this by kind of hooking into the eager PyTorch structures, and in a way that Torch Dynamo really needs to know about if it's going to work together with. Also, there's a blog down below if anyone wants more information. This introduces FSDP kind of pre-PyTorch 2. So naively, like if we just put these two things together, what happens? And so FSDP has a few things that are tricky. It replaces the module parameters with views into a flat buffer of parameters right before each forward call, and then puts them back to something else right after each forward call. And this is, again, so that it can orchestrate this like materializing just in time and then throwing things away just to save memory. And Dynamo needs to know about this. Dynamo tries to make some assumptions typically about Torch modules having the same parameters for a long time. Like if you compile a module, the parameters are probably going to stay there, and that's not true with FSDP. So Dynamo has to be updated to, or FSDP and Dynamo may need to be updated to coordinate better for this. Then communication ops, again, are happening both during forward and backwards. And I mentioned earlier, they're not traceable. So like we either need to make them traceable so we can put them in the graph, or we again need to graph break just so that they can happen in between the graphs. And finally, FSDP customizes the forward function of modules, and then also uses these hooks like before and after the backward functions run on modules. And Dynamo actually didn't know how to handle these hooks previously. So that's another thing that just has to be dealt with. And so all of this was a little bit more involved to get working than DDP. But if you want to see the full story of how it works, there's a stack of 4 PRs down below, and there's some illustrations and nitty-gritty details there. But the summary is that we have to graph break between FSDP modules, and that unblocks a lot of these issues. And we also have to make it so that FSDP and Dynamo cooperate a little bit, so that Dynamo is aware of what the right parameters are at any given time, like that FSDP is updating the parameters of a module, and Dynamo needs to make sure it's using the correct latest copy. So for FSDP, I don't have the graph of before, but this left graph is the speed up of using FSDP and Dynamo inductor together. This is the PyTorch 2 plus FSDP speed up. And so you can see it's above 1.0 all the time. In some cases, it's like for 8 GPUs, it's quite considerable speed ups, 1.6 for some of the models, and then more modest speed ups on some of the vision models. But FSDP isn't really used for accelerating models as much as for making bigger models fit in GPU. And so the memory usage of a model is a really important factor for FSDP. And PyTorch 2 has some additional features to target memory savings, which combine rather nicely with FSDP. So that's what explains the right graph. These models actually use less memory when you're using PyTorch 2 and FSDP together than they did if you were just using FSDP by itself. And the reason for that is because PyTorch 2 with AOT AutoGrad actually uses a minimum cut partition algorithm to choose to sometimes recompute gradients or activations during backwards instead of saving them. So it's a form of gradient checkpointing, but it's an automatic one that's part of PyTorch 2. So that's where I'll leave things. If there's any more questions, happy to take questions. And otherwise, thanks a lot.
Yeah. So to your last point about with the optimization, so it sounds like is it something that you get for free with just using PyTorch 2.0? It's like very low effort but high reward.
FSDP still requires you to tune a little bit. Like when you're applying it, you have to choose how to wrap your model. You have to choose which layers of your model to wrap together. And so you typically have to write some kind of a wrapping function. And that doesn't change with PyTorch 2. But and there are a couple other knobs you might have to tune in FSDP. So you will have to learn, like you can look at that FSDP blog and understand more about how to apply FSDP to your model. There are common patterns, like for transformer models, which are common ones to run. There are kind of pre-canned wrapper solutions that you can use that target transformer models with FSDP. But you may have to do some tuning.
Okay. Cool. So it's not exactly like very like no effort, but it takes a little bit of effort to get and a little bit of tuning. But once you do that, the benefits are huge. Just the speed ups that we saw.
Yeah, I mean the speed ups comes from the compiler again, and FSDP provides a way to reduce the memory usage so that you can fit a much bigger model. So the two systems work well together.
Yeah, yeah. If you're using I've spoken with a few people in the community that are using like just billions of images to do some really interesting things, and yeah, being able to have increased memory to do some training for that would be really beneficial. So more memory to store the stuff as you're doing the computations is very good.
Yep.
We had a question come in from Vat Shank asking, will the detensor implementation be involved with FSDP in the future? We saw a couple of RFCs talking about detensor plus pipeline tensor parallelism. Was curious if there was going to be FSDP support.
Yeah, so we're actually right in the midst of kind of examining what our options are for how to use traceable collectives and detensor and all these other primitives with PyTorch 2 for kind of a next generation stuff. And I don't have an answer for that yet, but hopefully we'll be able to share something soon.
Cool. And somebody, this calls back to another question. I think it was it was Karan who asked, and I shared a link in the chat to this, but I just want to call it out again, or call it out so people who are watching can know what he asked. But he basically said, thanks for the response about the traceable collective operators, and was wondering, like, he basically says this would have a big impact on 3P teams which implement custom process group backends. Is there a mechanism for co-designing these? And so I think this presents an opportunity for like contributing to PyTorch.
Yeah, absolutely. So I do encourage everyone to jump onto Dev Discuss. This is the link that's on the screen right now, and you can post there. Like we would love to hear more about like what your use cases are and collaborate on the design for traceable collectives.
Yeah, and so yeah, Dev Discuss is a good place to get that discussion going, and then yes, like that's one great thing about PyTorch is that it's open source, and so you yourself can become a contributor and a maintainer. So like if there's a feature that you're looking for or something that you want, and like you're like, hey, there's somebody that should be working on this. Maybe I can take a look at it. Like there's opportunities to do that with the open source model. So and we also had in a part of the PyTorch Live Q&A series, we did a talk on how and why to contribute tutorials and code to PyTorch. So I'm going to share a link to that in the chat, both to discuss, which is listed here on the slide, and then also to that video. Oh, and then Karan just asked another question. Says, thank you so much. Has a follow-up. Is there any timeline for when traceability is expected? And is the expectation that will improve performance?
So the timeline, I would say probably sometime this half, although we don't have a concrete timeline. And for the performance side, I don't think that for DDP it's going to do much, but for enabling like kind of more advanced things, it should unlock new possibilities. So we do hope that we can. I mean, there may be cases where it can improve the performance of existing solutions like DDP and FSDP, but I think it will also just unlock like more simpler implementations of these things that compose well with a compiler, and B, probably some newer versions of parallelism that are easier to implement if you start with a compiler and like the assumption that you have a graph.
Cool. This question came a little earlier in the presentation, but I didn't know when to interject with it. So sorry for taking a while to get to this one. This was from Subramanya, saying that is there a visualize for the backprop? And I think this was in relation to DDP, but I think FSDP also has a back. So is there a way to visualize? And maybe you showed that with the debug output, but
actually there is. I'm not sure if this is what you're asking about or not, but if I go to the slide on FSDP PRs that enabled FSDP, this last one, I think it's this one. We'll see in a second. Yeah, this PR contains a graph that shows the autograd graph. This is actually the dependency graph of backwards. And so I didn't dive into this level of detail before, but even after doing a bunch of things to make FSDP work, we thought I was all done, and still found that all reduces were in backwards were happening, or actually probably reduced scatters were happening way too late, and it was not clear why at all. And so I actually had to dump the autograd graph, and this graph shows like the it shows the dependencies of the grad operators in the backward stack, and like the red line is where I found that we were going, and the black line is where I thought we should be going. And so I had to understand that there's an ordering. Let me think how to explain it. And basically, the reverse order that tensors or operations get created in forward is saved in autograd's engine and used to determine the order that they will execute in during backwards. So there is a way to dump this view, and I think it is in my debug script still.
And is this debug script also part of PyTorch?
Yeah, this is all part of PyTorch. So yeah, this argument here that says torchviz, dump autograd graph with torchviz, this will get you that picture that I just showed.
Cool. That's nice. So then, yeah, you can look at that trace and try to figure out like, okay, why did it take this path rather than the one that I expected?
Right. And like this is only on the benchmark script, but you can also kind of read how this works and apply it to your own model.
Great. Let's see, any other questions in the chat? Those who are tuning in, we have about 5 minutes left. So if you have your questions, this is your last call for questions. So please go ahead and type them in the chat. Let's see, I'm looking through the history here to see if I missed any. Someone was asking about what GPUs are compatible with the current PyTorch version. I don't know. Do we have like an official list somewhere? I assume we do.
I mean, I don't know actually the exact list, but anything with tensor cores would be required for sure, like to use inductor. I think anything newer than SM86, if I remember offhand, is the architecture class we support. So typically like Volta and Ampere parts will work, but there may be some more nuance that I don't know the details of.
Yeah. Yeah, I think that's a good rule of thumb though. The Voltaire and I'm sorry, what was the other one that you mentioned?
Oh, Ampere.
Ampere, yeah.
And actually,
Cool.
like the newest class, the Hopper class, isn't supported yet, but will be, I think. It's just a matter of time for Triton support.
Cool. I haven't seen any other new questions pop up, so I'm willing to give people back time. There was one question about what Thursday's topic. Well, it says it's the QA on Thursday, different topic. I think, Karan, you might be in a different time zone because we are broadcasting around the world. It is the next broadcast is actually tomorrow, Wednesday, 11 a.m. Pacific time. So depending upon where you are in the world, it will be on Thursday. So yes, there's a, you can actually take a look. I'm going to go ahead and steal the screen from you. So if you go to pytorch.org/events, that has the list up of all of the different streams. And so yes, the next stream is taking place tomorrow at 11 a.m. Pacific time, and it's about Torch Inductor and how it integrates with PyTorch 2.0. So that's going to be a really cool stream. You've got several different engineers talking about that, and Shashank will be hosting that episode. So I would recommend bookmarking pytorch.org/events. And, if you scroll through the page, you can see, the upcoming schedules. And for each one, there's a link that you can click to register. So that way you'll get a notification when we go live, and you'll be able to not forget that you signed up to receive the notification. So let's see, got another question here. I'm not sure how to pronounce your name. It's XRP. It says, in regards to Thursday's broadcast, how long will it be for, and will Justin be there? Oh, okay. So I will not be hosting on Thursday. Actually, it's the next one is on Wednesday, the 25th, at 11 a.m. Pacific time. So depending upon where you are in the world, it might be Thursday, but the official date is the 25th, which is Wednesday. And Shashank will be hosting that, and we'll have speakers Natalia, Ben, Sherlock, and ICANN on the post. So yeah, thank you so much. All right, Will, thank you so much for your time. And yeah, if you want to say goodbye and sign off.
Yeah. Thanks everybody for your attention today, and look forward to hearing from you on the comments or on Dev Discuss.
All right, great. Thank you so much. And we'll see you tomorrow at 11 a.m. Pacific time.
Bye-bye.